So what did I do last time? So you start from a étale phi gamma module over OE, so it means torsion or torsion free. And you start from a unitary character of QP star. And then I define something that I called D cross delta P1, which comes with an action of G. G is GL2 of QP. So it was as a set, the set of couples Z1, Z2 in D cross D with some condition on ZP star. So if you restrict to ZP star Z2, then it is some W of delta applied to the restriction to ZP star of Z1, where this W of delta is some map, some OL linear map, continuous, going from D cross ZP star to D cross ZP star. And this, I remind you, is just D psi equals 0. And so this was defined by some very ugly formula that I'm not going to repeat because I don't use it. But you have an explicit formula. And I also, so I mean the action of G, you can be given by some skeleton of action by giving action on generators, so skeleton of actions, which is algebraic, meaning, I mean, it's finite formulas involving, so in phi, psi, action of the group gamma, and W of delta, and multiplication by 1 plus T to the B. So just involving this thing. So the main problem, I mean, there were two main problems, as I mentioned, is that this works for any dimension and any character, which is completely unreasonable. And so we are safe because this has not the right topological type. So it's not of the right topological type. And what we want is something which are of Barnard type, and this is of some extension of Banach by dual of Banach. And so we have to do something. And so to do something, I defined some other objects. So I had some commutative diagram of modules under the action of the mirabolic. So I had a restriction to QP map, which sent me to something that I had defined before, D cross QP. And inside D cross QP, I have the set of elements which are 0 at infinity. And in fact, they can be extended to elements here. So you have the D tilde here. And if you compose, you just have the natural inclusion. And inside here, I defined, so inside here you have this natural subspace, D natural cross QP. And so I defined some subspace here. So let's assume that D is torsion for this discussion, D cross delta P1, to be the inverse image of this one by this restriction map. And inside here, I had the D tilde plus, which was the set of elements of this one, which are 0 at infinity. So you have this diagram like this. And it is a commutative diagram under the action of the mirabolic. So everything, so commutative. For action of P of QP, which is, I remind you, the set of matrices of this type. so d tilde, so I mean you can define it intrinsically as a set of elements that goes to 0 at infinity in the sense I had mentioned, meaning that if you multiply by, if you if you let 1 be 0, 1 act, then it goes to 0 when b goes to infinity. But you can also get it directly from D by extending the scalars from OE to O tilde E. And so the so OE, I remind you, had something to do with functionalizing over ZP, and O tilde E is the same with functionalizing over QP, but going to 0 at infinity. So you have an intrinsic definition, and this tilde plus has also an intrinsic definition, meaning that it is going to be the set of elements in D tilde when you apply, which have no denominators, which you can test by saying that if you apply Frobenius, it does not, it stays bounded. Which? Ah? Yes. There are some elements with support at infinity. The element, yeah, so I described the kernel of this map here, which are exactly the element with support at infinity. And the kernel of this map, I remind you, was something like 0x, where x is in D and R, which was the intersection of the phi to the n of D. D tilde does not contain any of these elements. D tilde is a set of things which are 0 at infinity. So that's the kernel. So of kernel of this map restriction to QP. Well, anyway, so what is the point? So this everything is commutes with the action of the mirabolic, but it does not commute with the action of G altogether, and so it's not clear at all that this thing is stable under the action of G. So that's the main problem. So question. Is D natural cross P1 stable by G? So the only problem is to test it under the action of the element of the Weil group, 0, 1, 1, 0. So answer in general no. But so what we know is that it is equivalent. So this one is stable by G if and only if there is. So this if D is torsion, this is going to be open and compact. And so the statement that I gave you last time was this is stable if and only if there exists an M which is open and compact, stable by G. So if you have any open compact which is stable by G, this implies that this one is stable by G. And in fact, this one is the best possible stable by G because of the fact that if you look, so if stable by G, then if you look at the same thing for the Tate dual of D, and D cross P1, well, then they are exact orthogonal for the pairings that I define. So are exact orthogonal. For this pairing on P1. And so you have some kind of reflexivity here. And yeah, so maybe I should say that in general, they will, if this is stable by G, it will be the only one which is open and compact and stable by G. And if it is not the case, then if you take any other, it's going to differ by this one by some OL module of finite length. And so in general, you don't have finite length OL module which are stable by G, and so that's why. But it can happen that you have something a little bit bigger or a little bit smaller, and this causes some small problems in some. Well, anyway, so if stable by G, then you define pi of D to be the quotient D cross P1. Well, maybe, yeah, here I have a delta minus 1, and here I have a delta. Mod D natural cross P1. And now this has exactly the right topological type. Meaning the following. So if you start from something which is torsion, this is going to have the discrete topology. If you start from something which is an OL module, which is torsion-free over OE, what you get is something which is separated and complete for the p-adic topology. So it's going to be naturally the unit ball in some Banach space. Okay, so that's what I explained last time. What I did not explain was the following thing. So you have an exact sequence. Inside. So still, if you are in this situation where everything is stable by G, so you have an exact sequence like this. Just because of that over there. And the kernel is very small. So some map which I call residue at infinity. And so this is an exact sequence of P of QP module. So exact sequence and so I have to explain to you what is the action of P of QP on this one. So on this one, so this, I remind you, it's an OL module of finite length or finite type. And so the action of the unipotent is going to be trivial. So 1 B 0 1 Z equals Z. So on and so the action of ZP star is always the same. So what is not completely clear is how you define P to the K 0 0 1 Z. Well, what you do. So P to the K should be phi, but phi does not respect anything here. But phi is the inverse of psi, and psi is invertible here. So you just put psi minus K Z. And this is going to define an action of P of QP. And this plays the role of the Jacquet module in this situation. And what do you get from there? Well, from there you get something which so it has a right topological type, but you still don't know that it is admissible. But so what you get from this exact sequence is that this pi of D is finite length as an OL of, as a module over the mirabolic already, because this is and this is for a trivial reason. So pi of D is of finite length. Well, in case D is a torsion, finite length as OL of P of QP module. And so it is of finite length as OL of G module. Okay, and how do you prove this exact sequence? Well, what you prove is that if you look at the kernel of this residue infinity map, well, you can look at it I mean, you can compose with the projection from D cross P1 to pi of D. And then what you prove is that any element in a kernel can be written as a sum of an element in D tilde plus the sum of an element in D tilde plus, where you apply W. W is 0, 1, 1, 0. And what you prove also is that D natural cross P1, then this is equal to D tilde plus W D tilde plus. So this second statement you can believe. I mean, they are not difficult to prove. And this one, I just want to tell you what it gives in the trivial case. So if you start from D being OE, in that case, what you're just saying is that if you take a measure on P1, then it is a sum of a measure that goes to 0 at infinity plus a measure that goes to, that is almost 0 at 0. Okay, so that's what it says. Okay, so that's what I did last time. And now the question is, when is, so I mean, what we are interested in is the case of dimension 2. And so I stated the result in the following way. So the theorem is the following. And I will try to explain how it is proved. So we start from D frank 2 over OE. Yeah, maybe there is something I did not mention. So in case you have something which is torsion-free, the module which is here is not the inverse image here. You have to saturate it. So if you don't do that, in pi of D you could have some p torsion, and you don't really want that. So you just so if you take D around 2 over D, then you can define some character omega D, which is defined to be the determinant of D times x norm x minus 1. So the omega D is a character from QP star to OL star, and determinant of D is the character on QP star that you get on the one-dimensional representation attached to a determinant of D via local class field theory. And maybe I should just say that, I mean, in the local class field theory, that the normalization sends this character to the cyclotomic character, x norm x. And you can always reverse things. So, okay. And so I will just simplify a little bit the notation. So D cross omega D P1, I just call D cross P1. That will be a little bit less painful. And this W omega D, which goes from D cross CP star to go to ZP star, I will call just WD. So the theorem says the following thing. It says first that D natural cross P1 is stable by G. And second, it tells you that, well, now you have an exact sequence. So this D cross P1 lives in an exact sequence. So the kernel is this one, but this one is isomorphic to pi of D star tensor omega D. And when I say that, I mean, so you have action of G everywhere. And omega D means omega D composed with the determinant. And so where does this come from? So what you're going to get is that this D cross P1, if you look at this statement here, it's the dual of the same thing but with DH. But because we are in dimension 2, what we have is that DH is not naturally isomorphic, but it is isomorphic to D twisted by the character omega D minus 1. And because we are in dimension 2. And so what you would get from this one is that D natural cross P1 is the dual of pi of DH, but the dual of pi of DH is just the dual of pi twisted by omega t because of this isomorphism here. Okay, so so I explained to you where 2 comes from, and now I have to tell you how you can prove 1. And so that's the main point. And the proof of 1, I don't know any direct proof. So no direct proof. And so what we are going to do, so the strategy is going to be the following. So we are going to put D in a family. And then we are going to prove the statement for some Zariski dense subset of the family. And then we are going to deduce it from all members of the family. And so we are going to deduce for D itself. Okay. So the strategy is put D in a family. And then prove 1 for Zariski dense, so dense subset. And so this Zariski dense subset, you can choose either the crystalline D or the trianguline D. So we are going to choose the second thing, I will explain. And then it is quite formal to deduce 1 for every member of the family. And then deduce 1 for any element of the family. Yeah, so it's not very satisfactory, I have to say, especially that to prove. So this second step relies on quite ugly computations, but I think I have a way to avoid them now, but I'm not sure yet. So maybe.
Completely the person of invariance by this well group element obviously being multiplicated.
Yeah, you just need to prove that, yes. But I don't know how to prove it directly. Yes. I'm just about to. So what do I mean by family? So I start with some S, which are going to be some OL algebra. So it's going to be a quotient of something like OL with some variables. So typically it's the kind of algebra that you get when you look at deformations of things. Well, and you can take S equal OL is okay, but you're not going to stick to that case. Yes, so we are going to look at the formal spectral of this thing. So you have a maximal ideal, MS. And your S, you can write as a projective limit of S modulo ms to the n. So it's separated and complete for the ms topology. So this one you call Sn. And now this Sn is a finite OL. I mean, it's a finite algebra. Its finite length over OL is finite. Okay, so you look at X, the formal spectrum of S. So that will be the space of parameters. And so X of OL is also just the the set of morphism from S to OL. And you are going to denote by MS, M small s, the kernel. So this is going to be a prime ideal in S. So now you extend scalar. So you take the completed tensor product of S with our ring OE. So you defined it to be the projective limit of the Sn tensor OE over OL. Okay, and so you have a Frobenius, because you have a Frobenius here. So you define phi to be 1 tensor phi, and you define the action of gamma sigma A to be 1 tensor sigma A. Okay, and so now you have the notion of phi gamma étal phi gamma module on this ring here. So I mean the easiest thing to say is to say that so D you want it to be free of some rank, so free over
So now you want to be in the free case and not in a Dorfen case.
yeah. Now I want to be in the free case because I want to use well, I want to be in the free case. So free over S tensor hat OE.
The strategy would not work working with OL modulo over BU.
I don't think so. I mean, the main point is you need that. Okay, and the only way I know to have the Zariski dense subset for which I can prove things is really to work in characteristic 0. So I start from D free over S tensor OE, so with a phi and a gamma. And so what I mean by étal, so I just want that when you extend scalar from to Sn, so if you look at Sn tensor over Sd, then you get an Sn module of finite length. You get an Sn tensor OE module of finite length, but because Sn is of finite length over OL, then you just get also an étal phi gamma module. I mean, what you get is a phi gamma module over OE plus an action of Sn. Okay, and so you want this to belong to phi gamma torsion, étal torsion of for all n.
It's the same as telling that phi will give an isomorphism to some extent.
Exactly, it's the same. Okay. Yeah, and now if you have such a thing, you can also view it as a family of phi gamma module, because if you take an element x in D, you take an element S in X of OL, then you just define a ds by extension of scalar S modulo ms tensor over SD. And so one way of thinking about this situation is saying that this big D is just a big family that parameterize all these ds. And this ds is going to be an étal phi gamma module over OE. Okay, so what exactly. Yeah, and so in D you define a D natural, which is going to be the projective limit of the Sn tensor D natural. So and now if you are in rank 2, so now we assume that D is rank 2. Then you get, with the same formula as here, some omega D, which goes from QP star, but now it does not go to OL star, but it goes to S star. So it's...
with this sign, do you know anything about it to start with, whether it is free or horrible?
Which one, that?
Yes.
Well, I don't know anything about it, no. I mean, it's just compact. It's the only thing I know. It's compact and it's rather big because this, I mean, the transition maps are all surjectives. So, okay. And so, in particular, what happens is that when I evaluate at some point in X, then I get a surjection from D natural to DS natural. So it's rather big. Yeah, this functor D goes to D natural is not exact, but at least it's surjective. So if you have it's exact on the right. It's not exact in the middle, but on the right it's exact. So the theorem that we actually prove is the following. So it's the same theorem as here, but on a family. So what you prove is that this D natural cross P1. So maybe I should point out that that you can still form this D cross omega D P1 because you just take the formula in the projective limit and they pass to the projective limit. So you can look at D natural cross P1 and let's put NS because I don't want to saturate it. So so this is going to be the projective limit. To be the projective limit of the so Sn tensor D natural cross P1. So it's not necessarily saturated, this one.
The construction of this square, you have to distrain the argument of it, that in covariance by something infinity, because you want to make trains of variables.
Yes.
That's no problem.
That's absolutely no problem. I mean, it's at so the construction works at this level, okay, and then it passes to the projective limit by its per se, basically. So the theorem is that the first point, this is stable by the action of G. And the second thing is that, so you define pi of D to be the quotient. Okay. Yeah, and sorry, pi of, so okay, so you get a pi of d. And what you get is that this pi of d is going to parameterize some family of, of representations. So if you define pi of ds in the obvious way, yeah.
So you mod out by the non-saturated version?
Yeah, here I mod out by the non-saturated version. So I'm, yeah, I mean there can be some small p torsion that is left here. I mean in the argument it's better to do that. It's you could get rid of it, but it's a little bit of the pain in the arguments.
You might first make a limit and then divide by.
Well, what I can. I mean, the problem is that you would need to saturate not only for P but for the whole of S if you really want to do. I mean, yeah. So let me write something and then I explain what I want to say. So if you state some element S in in X, so what you get is that this ds natural cross P1 is stable by G. So you have a pi of ds by taking the quotient. And what you have is that this pi of d, so you have a natural map going from pi of d to pi of ds, just reduction modulo the ideal corresponding to S, or just evaluating at S, and this is surjective. So here you can have some p torsion that is left, or even, but here you killed it. So it's surjective for all S. And so what you have is a very nice family of representation of GL2 of QP that varies analytically with your point S in the base. So let me say something about this theorem. So going from 1 to 2 is rather formal. It's formal once you know that that this D natural surjects onto ds natural. So 1 to 2 is rather formal. And so yeah, and so what we are going to do is that we are going to explain that if 2 is true for a Zariski dense set of S, well, it will mean precisely here that if you look at the, so you have some family Sn, so you have some ideal MSN, and if you look at the intersection of all these things, it is 0. Yes?
I assume for the theorem you now take the triangular family or something?
Well, I mean, what I'm saying is that this theorem is true in any situation because because this theorem is going to be true everywhere. Okay, and but I'm explaining the logic here. So 1 implies 2, and 2, if you know that 2 is true for some Zariski dense family, then then 1 is going to be true. If 2 is true for some Zariski dense, it implies 1 is okay. I still have to produce some Zariski dense families for which it is true. Okay, but if I know, so yeah, and
you will first prove it for one family.
Yeah, so the idea is the following. So I will use a well-chosen family like this, and then this will allow me to prove it for any phi gamma module of rank 2. And then now if I take any family, then 1 is going to be true. Okay. But first I have to I mean, I don't know a priori that if I start from a random family, then I have a Zariski-Dance of set for which this is true. But I will first choose a nice one. So what kind of family do you take? Yeah, and maybe I should say that this statement is not difficult to prove. So what it uses basically is the fact that this functor D goes to D sharp cross QP. This one is exact. And then you have to know that D sharp cross tensor QP is not very far from this D natural cross P1. And not very far means that it is the same thing up to finite length things. So this part is not very difficult. But first I have to tell you what kind of family we are going to use. Okay, so what you do, you start from a D naught, which is arbitrary. So by Fontaine's equivalence of category, you have a V naught, which is a Galois representation. Okay, and then you can look at the space of deformation of V naught. So you're going to take X to be the space of deformation of V naught. Or V naught bar, sorry. So what I mean by that, for example, you can do many things, but one very easy thing to do is because this one is topologically finitely generated, instead of looking really at the space of representation, you look at the space of morphism into GL2. And then you have a nice, I mean, not so nice space, but you have a space. You're going to see representation many times because the automorphisms of the representation are going to act by conjugation on the but that's one way to do that. And then what you need to know, yes, so this is going to give you an S. And now what you take for D is going to be the phi gamma module attached. So yeah, sorry. So it gives you an S, and it gives you also a two-dimensional representation, Galois representation of GQP over S. Huh?
Very ignorant, but will this S be smooth?
Not almost all the time, yes.
But there you need a smooth S in the way you are explaining.
Well, no, I say it's a quotient of.
Oh, quotient, sorry.
So this space, I mean, it comes also with a vector bundle over it, which is equipped with an action of GQP. Okay, and so you take for D to be the D of this. Well, this one we call V. D of V. And this is going to be a phi gamma module. So this is an étal phi gamma module. Over, S tensor hat OE. I mean, the proof of Fontaine, I just have to copy it to this situation. There's not, there is nothing to do. In fact, it was done explicitly by John Dee, where he wanted to compute a Galois cohomology in a family, but there is basically nothing to do. and it's an étal, and it's free of rank 2. And now the upshot is that, in fact, the crystalline or triangulin point, so crystalline point, or trianguline. So I will define to you what triangulin means, and I will explain to you why they are directly dense, triangulin or triangulin points are dense. I think so, yes. In fact, I mean, most of the time, this space X, even when you mod out by the interaction, is going to be a ball, except in some cases. So the difficult cases is where this V naught mod P is an extension of what? Well, anyway, first of all, you can choose your lattice, so you are not in the difficult case of 1 by omega. So you don't want that. in that, see, if you look at the deformation of this problem, then it is not smooth. So you don't want this. But you can always put you in a situation where you start from your V naught, you extend scalar to, you invert P, then you choose the lattice so that the extension in the other direction. Omega is cyclotomic character mod P. So that one is more difficult to handle, so you don't want it. So if it is 1 by 1, that's where you use the fact that you have frame deformation. Yeah, you use frame deformations. And then it's going to be smooth if you use frame deformations. But there is one case where I don't know how to do what I'm saying, so I will explain to you. So crystalline points or triangulin points are dense. And so you can check it case by case. So there is one case that remains to be checked, which is the following. So remains to be checked. For P equals 2. And the semi-simplification, so V naught bar SS is delta plus delta. So it's a twist of the trivial representation. Well, maybe I put trivial tensor character. So basically, what you have to do, you have to understand the connected component of your space. That's the only thing. I mean, smoothness is not a problem. The problem is connected component, because you want to know what is the Zariski closure. And so what happens is that this space is connected, except for P equals 2, because for P equals 2, you see two connected components, because when you have this determinant and you look at the value on -1, then mod 2 you don't see the difference, but when you leave to characteristic 0, that gives you two connected components. And so Chenevier told me that he checked that, except in this case, what you get is really two balls. The space of Galois representation is two balls. And in this case, well, the space is really horrible. And nobody has actually computed it. But I mean, it's clear that there should be only two connected components. But this bad case is just you are in P equals 2, and you look at the deformation of something which semi-simplification is trivial. Trivial tensor with a character. The character is not going to play any role. So. Yeah, I mean, there are two cases which are complicated. The two cases which are complicated is the extension of 1 by omega and the extension of 1 by 1. Okay, and if P equals 2, these two complications just collide to make the situation even worse. So. So if anybody needs a problem, then he can try to compute actually the space of deformation here. Is the only one which is left. Okay. So that's how it works. And now I have to explain to you how you prove, how you will prove the triangle points are dense. So this it will use some infinite firm argument. But first I have to explain to you what these triangling representations are. Yeah, I'm sure you can do it directly. Yeah, you can, but I mean, people are so used of deforming. I mean, in fact, it's easy to deform Galois representation. I don't know how easy it is to write down deformations of phi gamma modules. I never tried, so. I mean, it's the same because you have an equivalence of categories, but I mean, you know, psychologically, it's better to work in one world. And also because periodic local long length is in fact an equivalence of category, you could also deform representation of GL2, but this I really don't know how to do. So. Okay, so yeah, so where is it? Yeah. So I want to explain what triangular representations are. So let me start. So maybe I start a new chapter, triangular representations. And unitary principal theory. So this one is a paper in asterisk 319. And this is a paper in asterisk 330. Okay, so let me describe you the content of this first paper first. So everything starts with a theorem of Kedlaya, which is some extensions of Dieudonné-Manin theory. So theorem of Kedlaya is the following. So you start from a phi gamma module over R. So D, a phi gamma module over R. No, well, phi module. D, a phi module. And étal, or phi module over R. So R is this row barring. So I remind you maybe that we have this E. So OE is a ring of integer of E. And inside the E, we have the subring of overconvergent element. And then we have this R, which is a row barring. So E dagger is the intersection of E and R. So you can view it either as a set of the subset of overconvergent element here, or you can view it as a subset of bounded elements here. So you have two descriptions. And so anyway, we start from a phi gamma module over R. And then Kedlaya tells you that, so which means the following. It means that it's going to be a free module of finite rank. And you want, so with a semi-linear action of phi, and you want, as usual, that phi of D generates D. So you want that phi of D. So if you extend the scalar R, tensor phi of R, phi of D, you have a natural map to D, and this is an isomorphism. And it's free also. Then the theorem is the following. First, there exists a unique filtration by sub-phi modules. So the first one is called D0 inside D1, inside the loop, inside DR, let's say. which is D, with the following properties. Well, there is no one. So this filtration should satisfy the following thing. So for all I, there exists some delta I inside the successive quotients. So inside di mod di minus 1. Yeah, so this di modulo di minus 1 is supposed to be torsion free as an R module. And so, in fact, it will be a consequence of what I'm going to say. So there is this delta I. So delta I is a sub E dagger module, so vector space, stable by phi. And which generates di modulo d minus 1, so such that when you extend the scalar from E dagger to R, then you get an isomorphism with di modulo di minus 1. And now, because you have a delta I, well, you can extend the scalar to E now. So E tensor E dagger delta I. And now you have a phi gamma module over E, so a phi module over E, and so it has slopes by the usual Dieudonné-Manin theory. And so you want it to be isoclean, so only one slope of slope, let's say, what is a good name for a slope? Well, it's Ri. And you want that the slopes are in a strictly increasing order. And Ri is less than R2. So this R is going to become an H, RH. So this plays the role of Dieudonné-Manin decomposition, but for phi modules of R. And as I said, when Kedlaya proved it, this was, the proof is very difficult. But now I think that Fontaine and Farg and Fontaine just put it under the So you put it under the hat of Ardan-Arashiman categories, and this pops out naturally. So okay, so everything here is unique, and the Ri that appear here are called the slope. Of D, so the slopes over R. And you say, so the definition of étal now is that, so phi D is étal if all the slopes are 0. So meaning that you have only one object in this filtration, and all the slopes are 0. If there is only one slope, which is 0. Okay? So we will take a break soon. Let me finish this hour by just making a very important remark. So the main point for me of this theorem is that you can actually construct things of slope 0 by starting with things which are not of slope 0. And so, so let me put it, so remark. So you can construct D of slope 0 starting with things which are not of slope 0. Non-zero slopes, zero slope objects. So that's the main point of this thing. So how do you do that? You see, you just have to take an extension which is in the wrong direction with respect to Kedlaya's filtration. And then if you have the right slope, it will force the slope to be 0. So let's give me an example. So let's take a delta from QP star to L star, which is not unitary this time. So you can define a figure module R of delta just by multiplying the action. So just multiply phi. So you have a phi on R by delta of P, and you multiply the action of sigma A by delta of A, if A is in ZP star. So you twist the trivial figure module by your character. And so you get something which is of rank 1. And so the slope, it's easy. So the slope is U of delta, which by definition is going to be a p-adic variation of delta of P. This is totally trivial. But now imagine that you are in the following situation. So if you have a figure module which is as the following shape, R of delta 1 goes to D, goes to R of delta 2, goes to 0. And if U of delta 1 is strictly bigger than 0 and U of delta 1 plus U of delta 2 is equal to 0, then you have a very good chance that D is of slope 0. Then D will almost all the time be of slope 0. I will give a precise statement later. What? Huh? Otherwise, it does not split. It could split when you invert T. Okay, so I mean, yeah, if it is not of slope 0, it means that you can not split this thing, but you can split T to the K. So T is always going to be log of 1 plus T. So multiplying by T and a figure module just means that you multiply the, it's just, so multiplication by T is also multiplication by the character X. So it means that if you take phi of T, because you get PT and sigma A of T, AT. So if you look at T times, or T to the K times the figure module, just the same thing as taking your figure module and twisting by this character to the power K. Okay. Okay, so let me finish with definition. So definition. You say that D is triangulable if it is a successive extension of things of rank 1. Of R of deltas. Yeah, maybe I should say that any figure module of rank 1 is of this shape. Maybe I put it somewhere. So any of rank 1 is R of delta for some delta. So why is this true? Well, I could not prove it directly, but you can go back to Fontaine's equivalence of categories, because inside here you will have. I mean, you can always twist it so that it has slope 0, and if it has slope 0, it corresponds to a Galois representation. So. Yeah, so you say that D is triangulable if it is a successive extension of R over delta. So this is a phi gamma module over R, okay? And now you say that D, which is a phi gamma module over E, or OE, you say that it is trianguline if the D-rig, so D-rig, what is it? I remind you. So you start from this phi gamma module over E. So you have an equivalence of categories with phi gamma modules over E dagger. So you take the subthing of over convergent element, and then you extend the scalar to R, okay? And so you say that it is trianguline if D-rig is triangulable. So on this level, you don't see at all that your phi gamma module is an extension of things of rank 1. Don't see it at all. I mean, this one can be, I mean, most of the time it will be really irreducible as a phi gamma module on object here. But when you extend the scalar of R, it will still be irreducible as a étal phi gamma module, but not as a phi gamma module. So it's trianguline if D-rig is triangulable. And you say that V, which is a Galois representation, is trianguline if D of V is trianguline. Okay, so in the next hour, I will study the trianguline representations, and then maybe if I have time, I will explain how they are related to unitary principal series. So maybe we come back in at 20. So it's not completely obvious from the definition, but it's not difficult to prove, is that if you are in dimension 2, something is triangulable if and only if there is some sub-object of dimension 1 in it. It's I mean, I'm not saying that this sub-object is saturated if you can produce one, but then it's easy to prove that you can saturate it in a rank 1 object. So anyway, so now you want to prove that you can actually construct things in this way. I mean, I just tell you if you have something like this, then it is of slope 0, but you have to prove that these things exist. So the theorem is the following. So you take two characters, delta 1, delta 2, and you want to compute the group of one extension of R of delta 2 with R of delta 1. So this is also the same thing as a group of extension of the trivial thing by R of delta 2, delta 1 minus 1. And just twist by delta 1 minus 1. And this is a vector space, so is an L vector space.
You mixed one and two.
What?
You mixed one and
Sorry.
one and
Delta 1 and delta 2 minus 1, yes. So it's an L vector space of dimension, well, either 1 or 2. So it's dimension 1, except in the following cases. Except if this delta 1 and delta 2 minus 1 is one of the two things. So it is either x minus I for I bigger than 0, or norm x, x to the I for I bigger than 1. So I is an integer. And in that case, in fact, it is of dimension 2, except where it is of dimension 2. And in fact, you have some natural isomorphisms that I will explain. So you have x of R with R of I, which is isomorphic naturally with x of R by R. And so you're looking at trivial extension of R by R, and this is exactly the same thing as OM of GQP to QP, if you look at Fontaine's equivalence of categories. And the same thing, if you look at x of R by R of norm x, x to the I, this one is isomorphic to the same thing as x of R by R x norm x. And this is dimension 2 because it corresponds to extension of the trivial representation by the cyclotomic character. Okay, so these are Kummer extensions. And because of this isomorphism, well, then this gives you an L invariant, which is Fontaine-Mazur in L invariant in this situation. So this isomorphism gives you an L invariant, which is Fontaine-Mazur L invariant. So this, I mean, there is a natural basis of this space of dimension 2. And if you, so you get a natural isomorphism between this and P1, and you have an L invariant, which is in P1 of L. What? This one is Fontaine-Mazur. Because, well, I mean, Mazur-Tate. Okay. No, wait. Mazur-Tate-Teitelbaum conjectured that there was such an invariant. And then there were many people who proposed some definition. So one was using phi gamma module, not phi gamma module, but phi and Filton module, which is Fontaine-Mazur, and which is exactly this one, in fact. There is one using periodic integration by Teitelbaum. And there is one by Breuil using periodic local Langlands. And maybe there are some other ones. I wrote a small paper to explain all the connections, but anyway, they are all the same. Okay, so how do you prove this kind of things? Well, I will assume that P is not 2, so that the gamma is procyclic. And then from phi gamma module D, you can attach the complex that I already wrote, the following complex. D goes to D plus D, goes to D, and goes to 0. Okay, and the map are the same as before. If you have a x here, you send it to gamma minus 1x, phi minus 1x. And if you have an AB here, you send it to phi minus 1b minus gamma minus 1a. So I remind you that this complex is the one that is used to compute Galois cohomology using figure module. Okay. So if D is a figure module étal over E or OE, let's say, then this computes the HI of GQP with value in the Galois representation attached to D. So we define, yeah, and so the H1 of this complex, in fact, computes the extension of the trivial by D. So X1, H1 of this complex, which I call H1 of D, computes X1 of R by D. And this isomorphism is very easy to describe. Assume that you have an extension D goes to E, goes to R, goes to 0. So here you have the element 1 here. You just lift it to some element E. And what you look at, well, the pair of elements that you will get here is just gamma minus 1 E, phi minus 1 E. This gives you a pair of elements there, which is in the kernel here, by construction. So this, I mean, this gives you a concrete description of X1. And I should say that Roche and Liu, I extended this result to, I mean, to compute X2 and so on. So basically extended the R thesis to the case of figure module over R. So now we are going to be interested in H1 of delta. So delta is a character from QP star to L star, by which I mean H1 of R of delta. And how do you study these things? Well, it will be two steps. So the first step is when U of delta is strictly negative, where I give a concrete description. And then there is this map delta, which is 1 plus T d over dt, which gives you a natural map. So it's what it does. It's something which is a Galois, I mean, which is equivariant from R of delta to R of X delta. Just multiplies the action of Frobenius by P, and it multiplies the action of gamma by A. So it gives you a map delta, which goes from H1 of X minus 1 delta to H1 of delta. And so you analyze this map. It's not difficult. And what you prove is the following. So this one is, so it's an isomorphism. Except in two cases. Except, so if delta is not one of the two things, so if it is not X or X norm X, so if delta equals X, what you get is that this map is identically 0, then delta is 0. But then you can compute directly the dimension, and you get that the dimension H1 of delta is of dimension 1. And if delta is norm x, x norm x, then you also have that delta is 0, but the H1 is dimension 2, as I said, of dimension 2. Okay, and this nabla here is the one that gives you these isomorphisms. So now, how do you deal with the case? Yeah. And what you get from this thing, if u of delta is strictly less than 0, what you get is that the dimension of H1 of delta is 1. And I will tell you how you prove these kind of things. So once you have this thing, I erase the theorem, I think, but once you have these results, it's easy to deduce the theorem. You know the dimension for u of delta strictly less than 0. If you apply a nabla, it just raise u of delta by 1, and so you get everything by this kind of thing. There is also a duality, yes. But yeah. I guess so, yes. Guys, so I mean, duality works here. I mean, I did not do any duality, but yeah. Yeah, so you have the usual duality that you have on Galois cohomology that extends to this setting. And so how do you deal with this case, for example? Then you can not only prove that it's dimension 1, but you can actually construct by hand a generator. And so let me explain to you how you do that. So you have two lemmas, small. So you start from measures. I assume u delta strictly negative. I mean, you won't see it. Yes. Maybe you will see it at some point. Well, I mean, for now, I don't assume it, but for the proposition, I will write down, I assume it. So you start from a measure on ZP star, and so most of the time you can just take the Dirac measure at 1. That simplifies the formulas. And then the first thing is that you can solve the following equation. So you can solve delta of gamma minus 1 b equals the integral over ZP star of 1 plus t to the x lambda. So this has a solution, a unique solution in E dagger. In fact, in E dagger, psi equals 0. And in fact, this is so maybe I should say that it's a special case of a general theorem. It's a special case of the fact that if you look at gamma minus 1, so gamma is any generator of our subgroup gamma. Well, this is invertible on D dagger psi equals 0, which is D dagger cross ZP star. So this is true for any phi gamma module. And this is one of the basic things that are used to prove duality in, I mean, to recover Poitou-Tate duality from this computation of the Galois cohomology. The fact that gamma minus 1 is invertible on this thing. So this, if you replace the dagger, if you remove the dagger, then this was in air scissors, and so we extended this with Charbonnier to deal with the general case. Okay, yeah, well, maybe I will come back to it next time. And now you want to know when is this solution integral. So this relation B has no denominator. If and only if you have that the integral over Zp star of delta minus 1 lambda is 0. So you get some subspace of k-dimension 1 for which you don't have, you have no denominator. And this is what is going to give you that the dimension of H1 of delta is 1. I mean, that's where it is going to come from. You have a space of codimension 1. So that's for the action of delta, of gamma. And then for phi, you have the following thing, that, well, you are going to assume that the integral over xi, over Zp star of xi lambda is 0 if, by any chance, delta of p is p minus I. Otherwise, you don't put any condition. Then this implies that if you want to solve the equation delta of p phi minus 1 A equals, so this you call A lambda, equals A lambda, then it has a unique solution in R plus. And this solution, yeah, and this solution is going to verify this condition in case you want this to, I mean, in case you are in this bad situation. And so how do you prove this kind of statement? Well, you just invert it formally, okay? So you're going to look at sum of delta of p phi to the n, so delta p to the n, phi to the n, a lambda. So if this has the good idea of converging, then you're done. It gives you a solution. And what happens is that if your a lambda is divisible by a big enough power of t, this is going to converge. And if not, what you do is that you solve by hand. I mean, you remove the first coordinates by subtracting something of the sum of alpha I, alpha j, t to the j. And here it's very easy. So by subtracting something like this, you can remove the first terms. And here it's very easy to solve this equation with something with a finite sum like this, because t is an eigenvector for the action of phi. So, so it's easy. And when you are here, the description of the cohomology is easy. So you see, I mean, by hand, by taking a solution B and A, you get an element in the C1 of this complex. And the proposition is that this gives you a basis for the cohomology. So the proposition is the following. Well, if you look at the A and B here, so A, B, so here you actually need that Vp of delta, that U of delta is strictly negative. AB is a basis of H1 of delta if you have this condition that the integral over Zp star of delta minus 1 lambda is non-zero. So it gives you everything you want, saying that you have you have dimension 1 and you also have a concrete basis with which you can do computations. Okay, so now that we have this at hand, then we can study the triangulin phi gamma modules. And so let me introduce the family of them. So we let S, well, maybe first we let T hat. So this is the variety of characters. So it's a, how do you call it? It's a formal scheme. So which is defined by the fact that T hat of anything is the space of characters from QP star to OL star, continuous characters. No, not to OL star, to L star. So it's so what happens is that a character of QP star, it's the value on P uniformizer plus the value on ZP star. So what you get is something which is the product of a ball by a GM. I mean, it's not a ball, it's a finite union of ball times GM. So this is a disjoint union of finite disjoint union of unit ball cross GM. Okay, and then what you do? Well, maybe you want a GM hat. I don't know. Anyway, I'm just going. No, you don't want a GM hat. Okay. Well, I'm just going to look at it as a set, but so yeah. So okay, let me write things, and then there are some things which I still don't know how to do. I did not look, but it's not uninteresting. So now you take T hat cross T hat. So you take two characters, and then you blow it up. So S is going to be T hat cross T hat, but it's blown up at some sub-varieties. So it's blown up at the varieties which appeared delta 1, delta 2 minus 1 equals xi norm x for I bigger than 1, and the varieties delta 1, delta 2 minus 1 equals x minus I for I bigger than 0. So these are exactly the pairs of deltas for which the dimension of the H1 is x1 is bigger than, it's not 1, it's 2, okay? And so so you have a map from S cross T hat to T hat. And now the fibers are either 1 point or 1 point. So this 1 point I call P naught of L, or P naught, which is just a point infinity. It's maybe not, or they are P1 in case you are over something of dimension of, I mean, if you are above one of these families. And if you, so you have a natural action of GM on this space. And so what you get, oh, sorry, on S. And so what you get is when you mod out, well, maybe I call it S tilde here. No, wait. Sorry. This one is S. It's okay. So what you can look at is S tilde, which is the space of extensions space of phi gamma modules of rank 2, so of triangulable phi gamma modules of rank 2 and which are not decomposable, so they are really extensions. So of non-decomposable, decomposable. So on this space, you have an action of GM. And because if you have an extension, you can multiply this extension by GM, and it will give you the same extension. I did not divide. Sorry, maybe. Well, okay. So that's not what I wanted. So this one is a space of extension. This S is a space of extension. And and the S tilde, which is above, is a space of delta 1, delta 2, and H, where H is an element in X1 of R of delta 2 by R of delta 1. And I have this map here, which is just mod out by GM, non-trivial extension. Okay, so a typical element in S will be called in this way. So it will be called S. And so you have two characters, delta 1, delta 2, which is the element here. And then you have an element L, which is an element in the fiber. And this L is most of the time infinity. And in particular cases, it's an element of P1, really P1. And so if you have an element S, then attached to it, you have a D of S, which is an extension of R of delta 2 by R of delta 1. So now we are going to be interested in the case where this D of S is of slope 0. Okay, so D of S is of slope 0. Well, this implies two things.
So this is a claim that those things fit together in this way. It's not obvious.
What?
That it's the same to look at delta 1, delta 2 plus a non-trivial extension up to a scalar, or to make a blow up.
No. So, I mean, one thing I don't know how to do. So this is a description point-wise of the space of extensions. Okay.
And point-wise is not obvious, because you have at least to identify those two P1, which you have.
No, but so, I mean, these two P1 are identified via the isomorphism that I put before. So I told. By the explicit construction. So if I get an element here, so I have, if I have something of dimension 2, by the explicit construction, I have a canonical basis, in fact. So
You hope you can do it in formal family?
yeah, so I mean, so the question is whether you can actually construct this phi gamma module over the entire space, which is here. So this I don't know. So that's the question. I mean, it's clearly true, but nobody has actually checked it. So. But it's a little bit strange. Because, okay, so assume you can do that. So you will have a four-dimensional families of phi gamma modules. Inside, you can cut the locus where it's slope 0. And then this is the same thing as some families of Galois representations. But if you look at what happens to the residual representation of this representation, then it jumps, really. So this is some kind of connected thing that connects all the deformation spaces of a Galois representation. So it's a little bit strange. But I think there is something to understand there. I mean, this is some kind of object that allows you to go from one connected component to another connected component of the space of Galois representation.
The thing you is that you take this extension you have of delta 1, delta 2, and if you converge to one of the backbones, and depending on the direction in which you converge, you get all possible.
Yes, you do. Yes, yes. This you can prove, yes. And in fact, you get in this way some formula for the L invariant in terms of derivatives of value, a special value of Frobenius, of eigenvalue of Frobenius. And this kind of formula, I think, was first noticed by Greenberg and Stevens, and that's how they prove some cases of Maser-Tate-Teitelbaum's conjecture. So, yeah. So, but let's come to our question. When is this one of slope 0? So you have two conditions that you have to satisfy. The first condition is that the determinant should be unitary. And so the first condition that the determinant should be unitary. So the determinant is going to be the product of delta 1, delta 2. So you get that the first thing is that u of delta 1 plus u of delta 2 has to be 0. Okay. And then the second condition comes from Kedlaya, because Kedlaya tells you that if by any chance this one has a strictly negative slope, then what you have here is the filtration that Kedlaya gives you. And so it cannot be of slope 0. So you need u of delta 1 to be bigger than 0. But that's not enough. But so we call S plus this space. And now we are going to cut some subspaces of this space.
The whole story you could as well fix delta 1 of the delta 2 be 1.
Not anymore, because it will not be of slope 0.
Oh, sorry.
Yeah. Before I could, but not anymore. So you define the weight of a character. So this is the Hodge-Tate weight of a character to be log of delta of u over log of u for any u in 1 plus 2 pzp, let's say. This is not going to depend on the choice of u, and so this is an element of, so delta is a character of QP star with value in L star, so this lives in L. So it's the hot state weight. And so you use it to define two things. So W of S is going to be, so in which sense does it go? W of delta 1 minus W of delta 2. So and then you define the following things. So S plus is going to be the disjoint union of S plus NG. NG is for non-geometric. S plus Chris. Chris is for crystalline. S plus ST. ST is for semi-stable. S plus ordinary. Union S plus NCL. This is for non-classical. And so how are they defined? So the first one is the easiest. So S plus NG is a set of S such that W of S is not an integer. So NG is for non-geometric. So it means that the weight of this thing is not an integer, and so it's not, does not come from the is not. So S plus Chris is going to be the set of S such that W of S belongs to n minus 0. So it's a strictly big positive integer. But then you want that U of S, so U of S is U of delta 1. So it's a p-adic valuation of delta 1 of P. So you ask that U of S is strictly smaller than W of S, and L is equal to infinity. S plus stable, so it's the same thing, except that you want that L not to be infinity. S plus odd. So what is it? You want U of S to be W of S. So the same thing, but you want that U of S is equal to W of S. And then finally you have S plus non-classical, where you want that U of S is strictly bigger than W of S. So this terminology comes from the classification of representation attached to over-convergent modular forms. So in this case, so U of S is the slope of Frobenius, W of S is the weight, and so there is a theorem of Coleman that if the, no, it's not the theorem of Coleman. Yeah, so one knows that, I mean, it's easy by using a phi and Filton module, that if the slope is strictly bigger than the weight, then it cannot come from a classical modular form. Okay, so that's why I call it non-classical. And here, well, I mean, in this situation, you recognize condition for representation to be either crystalline or semi-stable when it comes from modular forms. Finally, you have S plus, which is S star S0. And so here, the star just means that U of S is strictly bigger than 0. And S0 is means that U of S is equal to 0. And finally, you call S, well, truc machin. I don't think you have vocabulary that corresponds in English, so it's S truc. Yeah, but you have staff and staff, so staff and thing or something like that. Well, anyway, S machin. These are extremely useful French words. So if if you go to France and you say ce machin, ce truc, ce bidule, then you can go along. Okay, so let me describe you what you get in all these situations in terms of Galois representation. Yeah, and finally, so as I said, it's not true that everything is going to be of slope 0, but if d of s is of slope 0, then you define V of S to be the Galois, the associated Galois representation. Okay. So what is the theorem? So the first thing is that if S is in S star, then d of s is of slope 0 except in the non-classical case. So then d of s is of slope 0 except if s is non-classical, in which case the slopes are going to be u of s minus w of s and w of s minus u of s. So that's the first thing. So basically all the time you get really a Figma module of slope 0. I forgot to define the subspace which I call S irréductible, which is S star non-geometric with S star Chris with S star ST. So the second thing is that if S is in S irreducible, then the representation V of S is irreducible. So this implies that V of S is irreducible. And then the Hodge-Tate weights of V of S well, they are exactly the weights of the two characters. So they are W of delta 1, W delta 2. So if, in fact, this is true even if it is not irreducible. This last statement. What? Hodge-Tate sen, if you prefer, or generalized Hodge-Tate weights. These are the Hodge-Tate weights defined by sen. And if S is in S ordinary star, then what you get is that your representation V of S is not irreducible. So it is a twist by a character of something which is quasi-ordinary. So I don't know the terminology. So ordinary means extension of trivial by some power of cyclotomic character. Quasi-ordinary means extension of trivial by power of cyclotomic character times some finite order character. Okay. V of S is a twist of quasi-ordinary. Well, I would have the tendency to call quasi-ordinary ordinary. So, and finally, then you have almost no isomorphism between these things. So the only isomorphism that you are the following. So if you have V of S equals V of S prime with S prime. Yeah, but it's potentially on a abelian extension, blah, 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 and then you have something which is incredibly long to write. So with S not equal to S prime and SS prime in the irreducible locus, then what this implies, so this is if and only if, well, first you must have that L equals L prime equals infinity. So you cannot be in the semi-stable case. And, well, you have some relationship between the character. Delta 1 prime is equal to x W of S delta 2. And delta 2 prime is equal to x minus W of S delta 1. And you can check that, I mean, this operation that transforms delta 1, delta 2 into delta 1 prime, delta 2 prime, when you revert it, you go back to your, it's an involution. Okay, and then if you want something finer, what is better to do is twist. So you can twist by a character. So you twist by some unitary character so that delta 1 is trivial on ZP star. So that so it means that you have imposed one of the weight to be 0, one of the Hochstate weight to be 0, okay? But you have done a little bit better than that. You have imposed a little bit more, because Hochstate weight to be 0 would be just that on ZP star what you get is finite order, and here you really want to be trivial. Then the theorem is the following. So if S is non-classic, is not non-classical, then you can look at the decrease of V of S, and so it's non-zero, and it's even better than that. If you look at the part on which Frobenius acts by multiplication by delta 1 of P, then this is non-zero. And so this was basically the starting point of the theory, because so what Kissin proved is that if you start from over-convergent modular forms, then the Galois representation attached to them have exactly this property, okay? And and so I happened to be the referee of this paper, so I was forced to read it. And then later I found this interpretation in terms of triangulin representation. The second thing is that if S is in S star Chris, then V of S is Christabelline, which means that it becomes crystalline over some abelian extension of QP. If S is in S star ST, what you get is that V of S is semi-stable, but with a non-trivial n. So I mean that it is really semi-stable. It's not crystalline. Okay, so let me finish today by explaining to you how you prove that these triangulin representations are, yeah, maybe I should have pointed out that by construction, this V of S is triangulin. Huh? And so the space of triangulin representation is exactly the space of V of S by definition. So how do you prove that triangulin representations are dense? So here you have the space of representation. And so basically this is some ball. I mean, most of the time it's a ball of dimension 5. But anyway, it's of dimension 5. So space of representations, of Galois representations. So it's of dimension 5. So it's a disjoint union of these things, okay? And here you have the family of crystalline representations. So family of crystalline crystalline, but family of triangulin representations. And this is parametrized by some variety which is of dimension 4. So parametrized by S, which is of dimension 4. So you have your family here. And so what you prove is that if you start from a small point here, then so I mean on these varieties there is a natural analytic structure around each point. Okay, and what you can prove is that if you are close enough to one point here, then imagine that this point is going here, then you get some analytic, a small pitch which is analytic around here. Okay. So you don't really understand what happens, but what you get is that this big thing of dimension 4 is going to go in everything. And locally around every point, you have some kind of diffeomorphisms or isomorphism, analytic isomorphism. And so now what you have to know is that in each of these things you have a crystalline point. So you pick up a crystalline point. And if you have a crystalline point, well, a crystalline point is going to come from here, one point here. And so around the crystalline point, you're going to have a small piece of analytic of dimension 4. But this crystalline point, because of part 3, is going to come twice in the space. Okay, and so it means that when you project this space here, you have a second thing going from the same space. Okay, and now if you look at how the crystalline points are distributed, then what you can do is make the Hodge state weight go to infinity. And so around one crystalline point, you have a lot of other crystalline points. Okay, and from, through each of these new crystalline points, you have new leaves that comes. On each leaves, you have other infinite family of crystalline points, and so on. So that's the picture that Matthew drew. So he drew it in dimension 3 with the eigencurve. And here you have exactly the same picture in dimension 4 or 5. You don't see much difference, I think. But and so the point is that if you look at this picture, you see that you have too many double points. And so it cannot be contained into some subvariety of dimension 1. So it has to be the whole space. Okay. So I should mention that in a higher dimension, it seems that the result is still true, but it's much more difficult to prove. So it was proven by Chenevier. And also I think that Nakamura has also proved it. So same statement is true in higher dimension. So what you cannot do, so in higher dimension, the space that you are looking at is dimension d2 plus 1. Okay, but the space of trianguline is d minus. So it should be d minus 1 over 2. So that's the minus 1. That's the extension plus 2d. Is that okay? For d equals 2. It looks okay for d equals 2. Well, anyway, it's much smaller than that when d gets larger. So you can use this silly argument at the end saying that if it is not codimension 1, then it has to be the whole space, okay? So you have to work much more to understand how, I mean, so I think what Gaëtan does is that he looks at how these things fill up the tangent space at a crystalline point. And he proves that that they fill up everything. So. Okay, well, then I will speak of unitary representation next time. And that's it for today.